Welcome back to Partial Differential Equations. I'm Dr. Jeff Groh. We'll talk about the associated Legendre equation functions and series. The Legendre functions and the Legendre series. First we'll have the associated Legendre equation. It begins with 1 minus x squared y double prime minus 2x y prime plus n times n plus 1 minus m squared over 1 minus x squared y is equal to 0. Here, we'll have to take x values between -1 and 1. For the original Legendre equation, the only difference is m equals 0 in that case. We're going to generate Legendre functions that depend not only on m, but also on the parameter m. These will satisfy Ade-Rodriguez's formula, whereby Pnm of x is going to be -1 to the m times 1 minus x squared to the power of m divided by 2 times the mth order derivative of the Legendre polynomial of degree n. We have here then that Pn0 is the Legendre polynomial of degree n. M can take values of negative integers. M will take values between -n to n. So we need to define what happens if m is negative. We'll have -1 to the n plus m factorial over n minus m factorial times Pn minus m of x. So this will define the associated Legendre functions when m is negative, between -n and n. We have the theorem that if we have, say, I, m, and p, j, m, you get 0 if I is distinct from j. And also, when you take the inner product of p and m with itself, you end up with 2 over 2n plus 1, n plus m factorial over n minus m factorial. We are assuming here, of course, that m takes values from -n to n. In other words, these associated Legendre functions are going to be suitable for forming an orthonormal basis for a Fourier series. It is natural then to consider the approximation or the representation of piecewise smooth functions on the domain -1 to 1 with these associated Legendre functions. And the theorem is that if f is piecewise smooth on the closed interval from -1 to 1, then f is, in the sense almost everywhere, the sum as n goes from m to infinity of PNM of x. You find these Fourier coefficients in the usual way. We'll have to divide off the normalization factor and then the inner product of the function with the associated Legendre functions. This brings us back to the Dirichlet problem. We are going to assume that the boundary data depends only on the colatitude angle, theta. So if it doesn't depend upon the longitude, that means that we have a rotational symmetry. With this rotational symmetry, it's sufficient to choose the Legendre functions and not the associated Legendre functions in representing our solutions. It follows then that our solutions will depend upon A and R and theta, and will look like the sum as n goes from 0 to infinity of an, r over the radius a to the n, times these Legendre polynomials evaluated at cosine theta from our earlier work. Here, an is 2n plus 1 over 2 times the integral from negative 1 to 1. We're taking the inner product of our boundary data function with the Legendre polynomial evaluated at cosine theta. We'll have a weight on this inner product of sine theta. And here, n takes values in, I'll denote the whole numbers by the natural numbers including 0. Why is the weight sine theta? If you go back the lecture series, you'll find that the equation was theta prime prime plus the cotangent of theta times theta prime plus mu times theta equals 0. This is not in the standard Sturm-Liouville form. To do that, this is cosine over sine. We'll multiply through by sine theta. And then we'll have something that we can write as d theta times the sine of theta times our theta prime plus mu sine theta times our theta. You can see then that from the Sturm-Liouville theory point of view, the weight should be mu times sine theta, but mu being constant, and since we normalize our functions anyway, the mu's will cancel out. You only need to use sine theta. I'm going to plot some of these Legendre polynomials. This is an expression of the form r equals, I'm taking the complex modulus here, the absolute value, if you will, of the Legendre function of degree n and order 0. So these will be the regular Legendre functions and not the associated Legendre functions. Evaluated at the cosine of w, w will be our colatitude, which goes from 0 to pi. V will be the longitude, which goes from 0 to 2 pi. So as you can see, when n is equal to 0, we get this sphere. What happens if we choose n equal to 1? It looks like two spheres, one on top of the other. When n is equal to 2, you get this torus-shaped ring around the middle between these lobes which go up and down. Unfortunately, my program is not plotting the entire base of this. These are not spheres anymore. They pinch off towards the middle there. And when n equals 3, you get 2 of these bands, like that. For the general case, we'll have 0 equals the Laplacian of u, and in spherical coordinates, that's going to be the second order derivative of u with respect to r plus 1 over r ur plus 1 over r squared times u theta theta plus cotangent theta u theta plus cosecant squared theta u phi phi. In this case, we'll have u is r to the n times e to the I n phi times p n m cosine theta. However, we normalize these, and the normalization process will yield the so-called spherical harmonics. The spherical harmonics are going to be a capital Y in M. It's going to depend upon both phi and theta. And these are going to be let off by a factor of 2n plus 1 over 4 pi times the fraction n minus m factorial over n plus m factorial times the rest of this, e to the I n phi p n m of cosine theta. So the spherical harmonics are simply a representation of the last part of these, and we normalize this by this normalization factor to make our formulas simpler in the future. We of course have n taking values in the whole numbers, and m takes values in the set from negative n to n. One thing we should note is that both this solution and the spherical harmonics involve the imaginary unit I, so these are going to be complex valued. So in some of our formulas, we use inner products. Inner products with complex vector spaces are a little different from inner products with real vector spaces. The inner product with a complex space is going to be calculated with a complex conjugate. You may have a weight thrown in there too, but you have to throw in this complex conjugate on the second factor in the product. Because the conjugate only goes on the second factor, this won't be perfectly symmetric like in the real case. And so it doesn't end up being a true bilinear form anymore. It ends up being sesquilinear. Sesquilinear means 1.5 times linear. Yeah, we don't get that nice symmetry here. The theorem is, of course, then, that when we take the integral from 0 to 2 pi, 0 to pi, of the spherical harmonics, where we'll have theta phi and just some different values on n and m over here, with a weight of sine theta, d theta d phi, we'll get 0 provided either n is not n prime or m is not m prime. As long as one of those is different, these are going to be orthogonal. What happens if you have these being the same? There's a purpose for normalizing. And that is, you get 1. That means these spherical harmonics will, in some sense, form an orthonormal basis, at least in theta phi space. The theorem, then, is that if f, as a function of theta and phi, where, of course, we're assuming that theta goes between 0 and pi, phi goes between 0 and 2 pi, and f is 2 pi periodic in phi, so that things match up when you go all the way around. And also, f is sufficiently smooth we'll suppose that it can have discontinuities at places, but there are only jump discontinuities in a certain sense. So if f is sufficiently smooth, then this function will in fact have a representation. M goes from 0 to infinity, m goes from minus n to n. We'll have a n m as our coefficients to these spherical harmonics, where, how do you calculate these Fourier coefficients? Well, you do it in the obvious way, and since we have an orthonormal basis now, we don't need to have a normalization factor. It's just going to be the inner product. We'll have our function. Since y is in the second position, it's going to have a complex conjugate. Where the weight is still sine theta, and so you can see it's easy to calculate the Fourier coefficients in this case. It follows then that the solution to the Dirichlet problem on the ball is a n m r over a to the n. We'll just use the spherical harmonics where we find the Fourier coefficients a n m from the boundary data. We must have, if r equals a, so this will be a 1, we'll get the boundary data. And we can pick these off by simply taking the inner product on both sides with respect to the spherical harmonics, remembering to use the complex conjugate when you do the integral. We could have derived the spherical harmonics from its own differential equation. Recall that the differential equation begins with second order partial of u with respect to r, 1 over r ur plus 1 over r squared times u theta theta plus the cotangent of theta u theta plus cosecant squared theta times u phi phi, all equal to 0. In this case, we could have made the separability assumption that u factors as a function of r times the spherical harmonic with respect to, say, theta and phi. If you plug this into the partial differential equation up here, you'll have r prime prime times big Y, 1 over r prime times big Y, 1 over r squared. You'll have y theta theta plus cotangent theta y theta plus cosecant squared theta y phi phi. If you now divide through by r y, you'll end up with an over r, and this will cancel. Over r, this will cancel. Oh, these shouldn't have r's. If we're now dividing these r's out, those will all go, and this whole thing will then be divided by a big Y. We can then separate the variables. We'll have r prime prime over r, 1 over r prime over r. With everything else moved over to the other side of the equation, this will have to be a constant. We'll call the constant mu as before. You'll recall that these are n times n plus 1. And so then we can write down the differential equation on the y's. We can multiply this y onto the other side. We'll have, remember, all of this stuff becomes a negative. We'll move the negative over as well. We'll have y theta theta plus cotangent theta times y theta plus cosecant squared theta times y phi phi equals minus mu times y, multiplying this y over with the minus mu. This gives us an eigenfunction problem. And we can show that this has non-trivial solutions if mu has the form n times n plus 1, to each acceptable mu, there will exist 2n plus 1 non-trivial solutions y n m, where m will have to take values between negative n and n. These will be exactly the spherical harmonics as we have previously described them. In our next lecture, we'll apply this solution method with spherical harmonics to, say, the Helmholtz equation, the heat equation, the wave equation, all with spherical coordinates.